কোর্স আউটলাইন যেটা দেয়া আছে ওখানে সিলেবাসটা মেনশন করা আছে। কেউ ইমেইলও করছো আবার সিলেবাস নিয়ে। আসলে তো আমাদের কোর্স আউটলাইনটা ক্লাসের লেকচারের শুরুতেই দেয়া হয়। এখানে দেখো ভাগ করা আছে আমাদের যে মিড টার্ম কতটুকু হবে, ফাইনাল কতটুকু হবে। তো মিড টার্ম আমরা এ পর্যন্ত ছিল আমাদের মিড টার্ম। That means up to the constant satisfaction problem. Then the next is final. So here final out of here 35 marks out of 100. Okay? The first thing is about the learning in AI, the introduction to machine learning, that chapter, and also the neural network, backpropagations. These are the syllabus it will cover the in our final exam. So you can see from this chapter total 10 marks will cover. Okay, that means I will set the question for 10 marks. And then the advanced application, you can see computer vision. Specifically, we discussed about the deep learning and convolutional neural networks. Okay, we have discussed the deep learning here also. This is the deep learning, and here also advanced deep learning, specifically the convolutional neural network. And it will carry 5 marks. And then the knowledge base and also the planning, I will discuss a little about these two in today's lecture. And then the next is our reasoning and uncertainty. Here already we have discussed about the hidden Markov models. I think you understand the hidden Markov models, but you have some questions here. So I will discuss few of the questions of hidden Markov model. Then we also cover the reinforcement learning. And in reinforcement learning, you can see 4 marks. And from here it is 6 marks. Okay. And the part of the planning, actually, we have already discussed in hidden Markov model. So just I will discuss a little about the planning, how it is related to this hidden Markov model and all other probabilistic reasoning. So that's all in our final exam syllabus. So 10, 5, 5, then 5, 6, and 4. So total 35 marks. So you have one question regarding HMM. At first, I want to discuss it. So there are some given probabilities, initial probabilities, transition probabilities, and emission probabilities. But how can we calculate those probabilities, or how can we get those probabilities? So as I already mentioned, in some questions, maybe the model will be given. That means those probabilities will be given, and you will be asked for finding out the state sequence based on the observation sequence. Okay, that means you have to apply the Viterbi algorithm for that. And in some cases, the data set will be given, and you have to find out those probabilities and the model. And then, based on those probabilities and the model, again, the observation sequence will be given. And based on the observation sequence, you have to find out the state sequence utilizing the Viterbi algorithm. So how can we find out the probabilities if the data set is given? It's easy, but I think you have some confusion on it. So let's say a data set is this. This one is a data set. This is given. This is actually the weather model data set. If you can remember that we have the observation just the rainy day or maybe dry day, and we want to find out the atmospheric pressure of the day. That means whether the atmospheric pressure is high or low. So that's why in this case it is mentioned that the observations are rain and dry. and the states are high atmospheric pressure and low atmospheric pressure. Okay, and now we can see that this is the data set. This data set, it is mentioned that the timestamp is given. Let's say this is day 1, this is day 2, up to day 7. And this is first week, second week, third week, fourth week, and fifth week. Let's say just 1 month's data we have collected. And this is the observation sequence of first week. In first day, the rain, second day rain, third day rain, like this way, okay. Day 7 also rain. In second week, the first day of second week is the dry day, rainy day, dry day, like this way, okay. Similarly, the third week is here, that is rainy, dry, dry, okay. So those are the observation sequence of fourth week. And third week, then fourth week is rain, 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 dry, dry, and fifth week's observation sequence is dry, rain, dry, 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 like this. Okay, so these are the observation sequence given for the first week, second week, third week, fourth week, and fifth week. Now, what else is given here? That means from the weather station, it is also collected that the atmospheric pressure of the day. So that's why on the first day of the first week, the weather station mentioned that today's atmospheric pressure is high. So that's why it is mentioned. The next day, it is lower. The weather station mentioned that. Day 3, we have collected the data from weather station and mentioned that the low atmospheric pressure. Fourth day is high atmospheric pressure. In this way, okay. Similarly, for maybe you can say the last week, the fifth week, the first day of fifth week, the atmospheric pressure, it was high, and second it was high, third it was high, like this way. Okay. So this is the data set given. Now we want to find out the initial probability. That is the initial probability of high atmospheric pressure and initial probability of low atmospheric pressure. So initial probability of high atmospheric pressure, if we want to determine that. And then initial means you have to just check the first day. This is the initial day. Okay, so the first is the initial day. So initial probability, if we want to find out the initial probability of high atmospheric pressure on the first day of first week, second week, third week, fourth week. In the first day, how many times we got the H? That is high atmospheric pressure. We can see this is H. Here is also H. Just only 2 days. Okay, 2 days. So that means 2 out of how many weeks? We can see 5 weeks. Okay, out of 5. So this is the initial probability of high atmospheric pressure. Similarly, we have to find out the initial probability of low atmospheric pressure. On that case, we have to find out how many times on the day 1 the low is mentioned. You can see 3. Okay, so 3 out of 5 days. So this is initial probability of low atmospheric pressure. The summation of initial probability of high and initial probability of low must be 1. Okay, if we sum up initial probability of high, initial probability of low, then you must get 1. Okay, so we got the initial probability. Now the transition probability. So you want to find out the transition probability among the states. Okay, transition probability. So let's say we want to find out the transition probability. So transition probability high to high. Okay? High to high. So transition probability high to high. How can we determine that? So that means you want to find out the transition probability from high, let's say high to low. You want to find out this high to low. What will be that? So now from the first day, you have to see how many times these kind of transitions are there. That is from high to low. You can see okay the high to low. So this is the first is high, second is low. So this is one transition, high to low transition. And here is the second day is low, third day is low. So that means this is low to low transition. Then third day to fourth day is low to high. Fourth day to fifth day, it is high to high. And fifth day to sixth day, it is high to low. Okay, so that means this is high to low. So another one we got. And then sixth day and seventh day is low to high. Okay, no. First week, we already got two. And in second week, low to low, and then low to high, and then high to high, then high to high, then high to low. So this is another one, high to low, then low to high. No, second week, that's only one. In third week, we can see low to high, high to high, high to high, high to high, high to low. This is fourth one, okay, and low to high. And then we have low to low, low to high, high to high, high to low. This is another one. And low to high and high to low. This is another one. Okay. And then high to high, high to high, high to low. So this is another one. And low to low, low to high, high to low. So here is another one. 1, 2, 3, 4, 5, 6, 7, 8. So total 8 out of. Okay, now we have to see how many times the transition starts from age. How many times the transitions starts from age. Okay, so this is the transition, the transition from high to low, but sometimes you will get that high to high also. Okay? High to high, this kind of transitions. That's why we need to count how many times the transition starts from age. So now you can see H to L. So this is one time. L to L, no. L to L, no. H to H. So this is another time. Transition starts from H. And H to L. So this transition also starts from H. And low to high, no. We should not consider this because we can see there is no transition from H because this is the last day of the week. So there is no transition, okay, for that case. So that's why we should not consider this H as a transition. Here is L, L, then this is H, transition from H to H. This is another one, transition from H to H. So here is also transition from H to L. Then we should not count it, okay? So how many already we got? 1, 2, 3, and then 4, 5, 6. We have already got 6. 6, then we can see here is 7, 8, 9, 10, okay, 10, then 11, 12, 13, then 14, 15, 16, then 17, okay, total 17. So out of total 17 8 that will start a transition, 8 times we got transitions from H to L. So that's why the probability of transition from H to L is 8 by 17. Similarly, you have to count for others also. That is probability of L to L, probability of H to H. Okay. So this is transition probability, and last one is emission probability. Okay, emission probability. That means we want to find out the probability of there is rain given, maybe you can say given high atmospheric pressure. Probability of rain given high atmospheric pressure. So that means the HR. So we have to count the HR combinations. So HR combination, like the first day, we can say this is one of the HR combination. The high atmospheric pressure, and we observe the rain on the day. Low atmospheric pressure, rain of the no, that's not that. That is HR combination. So here is another HR combination. HR, this is another HR combination. The two, this is third HR combination. 3. Then LD, LR, HD, HD. Here is another one, HR combination. There is 3. LR, HD. This is LR, HD, HD, HD. Here is HR also. And LD, here is also another HR. Here is LR, LR. This is HR. Here is also another HR. Here is HR combinations. Okay. So now count the total number of HR combinations we have. I didn't count it. Okay. So you need to count how many times the HR combinations is there. Okay. And now you have to count also another, that is total number of H. Okay. That is HR can be, combinations can be from H to R and H to dry. Okay. So 2 types. So you will get the HR combinations and you will get the HD combinations. But you have to now count how many times just we get the H. Okay. So how many times H? We can see in previous example, the H here is total 17, but we just exclude the H of last days. So we can maybe you can say we can include, here is H, here is H, 3. The total maybe you will get 20 H. Sometimes you will get HR and sometimes you will get HD. Okay, this is how you can compute the emission probabilities. Is it clear now?
Yes, sir.
Okay. Okay, now I think I want to discuss a little about our knowledge representation. So in case of our knowledge representation, we have to represent the knowledge of AI. Okay, knowledge of AI using some form of form in some forms. Okay, so that the forms we will discuss here, specifically the propositional logic and first order logic, these 2 types. Okay, so knowledge can be represented using the propositional logic and knowledge can be represented using the first order logic. There are some other knowledge representation methods also, those are advanced methods. But in your syllabus, these 2 things you need to understand. So I think most of you already know these things because actually the logics in our programming knowledge we already have. So I think it will be easy for you. So logical constants. Specifically, logic can be true and logic can be false. Okay, so any statements, if we want to think about just an statement, the statement can be true, or it can be false. So that's why the in our case, the logical constants, those can be either true or maybe the false, okay? Or maybe the false. The propositional symbols for knowledge representation, usually different symbols we can use, like most of the case we use a P, Q, S, R. Okay, those uh, symbols usually we use for atomic sentences. And sometimes we also use the wrapping parenthesis. That means we can say just the parenthesis sometimes we also used in knowledge representation. And some of the symbols you will find out in our propositional logic also. That is that this is and symbol, or symbol, implies symbol, equivalent symbol, and not symbol. So atomic sentence or negated atomic sentence you will get in our knowledge representation. So if we can see some example, P means it's hot. Okay, so just one statement, atomic sentence, it's hot. You can represent Q means it's humid, and R means it's raining. Okay, then you want to represent this one, this statement, using a form. This is called the propositional logical form. So if it is hot and humid, okay, so P means hot, and Q means it's humid. So we can see that if here is the P means hot and Q is humid, so P and Q, so if it is hot and humid, then it's raining. Okay, so here is R is there. Okay, so that means this is the implication sign. Okay, P and Q, that means hot and humid, implies raining. So that statement, this statement we can represent using this propositional logic. Okay, that is P and Q implies R. It means P is it's hot, and Q is it's humid, and R is it's raining. So if we can represent one statement, that is, if it is hot and humid, then it's raining, then this is the form to represent the knowledge using propositional logic. Okay, and if we want to represent another statement, like if it is humid, then it is hot. So we can say humid it means Q, and hot is P. So we can write that knowledge like this one. That is Q implies P. Okay, Q implies P. Okay. So that's why in propositional logic, what usually we do, the sentences, those are atomic sentences. The atomic sentences usually is an every part of the sentence or every sentence usually we define a symbol for that, and then we write those sentences uh, for complex representation of propositional logics. So a sentence can have the BNF form. We call it a sentence can be atomic sentence, or it can be complex sentence. The atomic sentence, it can be true or it can be false, or it can represent using some symbolic representation like P, Q, and R. The complex sentence, Usually it can be just a sentence, or it can be sentence, then some connectives, and then again sentence. And sometimes we also represent the complex sentence as not, then again sentence. So here connectives are, that means to connect several sentences, usually we use not, and, or, implies, equivalent, those signs. So I think we have already know what are these means. That is, for and, usually we use this symbol. For or, usually we use this symbol. For imply, we use this symbol. For equivalent, usually with this symbol. And for not, usually we use this symbol. Okay. So now the valid sentence, or usually we call it tautology. That means if a sentence it is always true, then that kind of sentence is called tautology. Okay, tautology. The earth is moving around the sun. This is universal truth. Okay, so this is a tautology. Now another form, like it's raining or it's not raining. If this is the sentence, this is also tautology. Okay, it's raining or it's not raining. This is tautology. But some sentences usually we call also the contradiction. Okay? Contradiction. So those sentences are always kind of the false. Okay, like it's raining and it's not raining. So that means it's raining. Someone said that it's raining and it's not raining. That means two statements cannot be true at the same time. Okay, so it's raining, either it's raining, or if we can mention here or, then this is the tautology. Okay, but we mention here and, so that means this is a contradiction. Sometimes we also mention about the entiles. Okay, P entiles Q. Usually we write in this form here. This one is called entiles or entilement. It means whenever P is true, so is Q. Okay, so whenever P is true, then so is Q. So in other words, we can say for all models of P are also models of Q. Okay? So that's what we call P entiles Q. For the propositional logic, usually we can represent those using some kind of truth tables. I think most of you already know about the truth tables. So if we have two variables like P and Q, that means P represents some statement, Q represents some sentence or a statement. Then if we have the AND operation, okay, AND operation, then if both of these are true, only on that time we can say that the statement is true. Okay, P and Q, two statements. If we join using maybe AND operator, then if both of these statements are true, then only on the time you can say this is true statement. Okay, so that is the case. For other any, maybe one statement is false and another statement is true, on that case all the times it will be false, because the conjunction here is the connectivities here is the AND. But for the or, P or Q, that means only one, if one statement is true, then another is true. So here is we can see for this case true, if here is a true and here is also true. So if any of the statement is true, then we will say for the case of the or, it is true. Okay, so dot or and. Okay, and only false when both of these are false. And sometimes we represent using the if then else rules. It is implies, implication. P implies Q. So P implies Q in this form. So that means if P then Q, or we can write this one also. It is same as not P or Q. Okay. So the implies means it's not P or Q, not P or Q. So that means this implication will be true when it will be true For the case of the true and true, it will be true. Okay, so that means we can see not P. If we not P, that means if we not this one, then it will be false. And or Q, so or this is T or true. So that means one is true. So in case of the or, if one is true, then it will be true. But how about this? Not P, that means it will be false. It will be false. And or F, that is, here is F and here is F. That means it will be F on that case. For other case, like this is F, so if not P, it will be true for that case. So true for that case. And here is also true. True or true is true. And then here is F, that means not P, that means it will be F. And so it will be true. And here is F. So true or false, as it is or connection. So that means we can say we will get the truth. So this is called the truth table for P implies Q, or if P then Q. And for not, this is the negation. Okay, so not true is false and not false is true. So this is just negation truth table. So in this way, we can also see, that means, okay, this statement, all those statements already we got the result. That is not P, P and Q, P or Q, P implies Q. Here is a P equal Q or equivalent Q. So for this case, actually it is two representation. P implies Q and also Q implies P. Q implies P. So this is the representation for that. So for this one, actually we have to check this one as not P or Q. And this one is not Q or P. So then we have to connect this one with AND notation. Then you will find the result. Okay. So if both of the case we will get true, then only the true, otherwise false. Okay, so you will get this one. And the complex sentence can be written also using the propositional logic. Okay, and for that, on that case, the truth table will be like this. So here is the PQ, and we can see some of the complex sentence. This one, we can consider this one. Here is P or here's the P or H and not H. Okay, so it means P or H. So this is the P or H and not H. So not H, this is the H. But if we can say that not H, that means false will be true. So this will be true here. This will be false. And false will be true. False will be true. And true will be false. Okay. So then the connectivity here is and connectivity. Okay. So that means if these two, both of these are true, then only we will get true. So we can see here is the false and this, there is the true, so it will be false. Here is the false, here is the true, false, true and true. That means this time we will get the true. And here is the false, here is the true. That means this is false. Okay. So even though we get the complex sentence, complex representation using our propositional logic, then we will get also the statements true. Okay. I think the propositional logic we can discuss up to here. And then I think it's better if we can go for our first order logic. Okay, the first order. Why we need the first order logic? What's the problem in propositional logic? So we already have seen the propositional logic, but what's the problem there? The propositional logic, specifically those one are not sufficient to represent the complex sentences with with some real natural language statements. Okay, so it means that only can represent the facts. Okay, that is it can only represent the facts, whether it is true or false. The propositional logic is not sufficient to represent the complex sentences or natural language statements. So that's why it has limited expressive power. Okay, limited expressive power. So we need something extra. Okay, something extra to represent our different kind of natural languages. Like if the statement is this: some humans are intelligent. Okay, propositional logic just only can say that, okay, this is true or false, like this. And Shoshin like crickets. Okay, Shoshin likes cricket. So then again, we can say this is this statement is true or false. Using the propositional logic, we can represent, but we cannot represent the structure of this sentence, like Shoshin like crickets. And also it has no statement of quantifiers. Okay, in propositional logic, that means some of the people, all of the people, so for all, so those kind of representation is absent in propositional logic. But we can actually get those in our first order logical statements. In first order logic, so we have the objects usually. So any number, any people that can considered as the objects, like A, B, people, numbers, colors. Okay? And in first order logic, we can have the relations also. Okay? Relations also. That means the relations can be unary. That is that if the color is red, round, the brother of, sister of, so those kind of. And also the function, like the father of, best friend. So we can represent the first order logic using those functions also. Like the natural language, in first order logic, we have syntax and also semantics. So the basic elements of the first order logical syntax are the constants, the variables, predicates, functions, connectives, equality, and quantifier. So we already know about the connectives from the first order logic. And the constant here, that means any value or number. Okay, so those, any name, those are our constants. And those can be represented using some variables, x, y, z, like this. And some function like a square root, left leg of, okay. And some predicates can be like brother, father, greater than, smaller than. Equality also in our propositional logic. But these quantifiers, okay, for all, and they exist. So this is for all, and this is their exist. Okay, so these are the quantifiers in first order logic. So let's see some of the examples. Like one example is Ravi and Ajoy are brothers. So if we want to represent this one in first order logic, then usually we write like this way. So brother is our relation. So Ravi is the brother of Ajoy. Okay, so this is statement. This is the representation of first order logic. The Ravi, brothers of Ajoy. Then Chinky is a cat. We can represent this one is the Chinky is a cat. So the cat, the name of the cat is Chinky. Okay? The Chinky is a cat. So this kind of representation we call it first order logical statement. So that's why even the complex sentences we can represent using the first order logics. In case of the statement, in first order logic, it has two parts. One, the first part is called the statement, okay. And second part usually we call it is predicate. So in any statement like x is an integer, x is an integer. For this case, this is the subject, x is the subject, and integer is our predicate. Okay, so that's why it is mentioned this s. X is a subject and is an integer. This one is predicate. Then the representation for this, we will use those subjects and predicates relationship. So like if we can say that x is an integer, so that means we will see that integer x. Okay, so this is subject and this is predicate. Okay, so two types of quantifier we can also use in propositional logic. One is universal quantifier and another is existential quantifier. So universal quantifier is called for all, everyone, everything. And existential quantifier, usually we call it like for some, at least one, like this. Then if x is a variable, then this representation, this is our universal quantifier x. So universal quantifier x, it means for all x. So that's for all x or for each x or for every x. So this is represented by this universal quantifier. And universal quantifier usually it uses the implications. Okay, it's used the implication. Like if we want to represent this one, all men drink coffee. So all men drink coffee. So if you want to represent this one using the universal quantifier, so all men, we can see in this case we can represent each one. It is for all x. The x, this is the variable x. Actually, we can say x can be any man. Okay, any man. It can be x1, x2, x3, any man. So that's why it is represented for all x, where x is what? X is man. X is man. For all x, that means for all men. It implies, that means for all men, drinks coffee. Okay, so drinks, so drinks, and then drinks, that means x man drinks coffee. Okay, so that's the representation here. Okay, so that means x drink coffee. So that means if we can say if x is a man, then x drink coffee. Okay, if x is a man, then x drink coffee, and this is true for all men. Okay, so that's the representation. Usually we read it like this: there are all x, where x is man who drink coffee. Okay, so we read like this way. So for all x, where x is man, and x, then x will drink coffee. The another quantifier is usually called it is existential quantifier. So this is existential quantifier. Okay. Then it represents there exists x, or for some x, or for at least one x, like this. These representations. Some boys are intelligent. If we want to write this statement, some boys. So some, that means not all. So for that case, what we have to do? There exists some x. There exists some x where x is boys. There exists some x are just boys. Okay. It implies that. It implies. Okay. Not implies. Usually in existential quantifier we use the and. Okay. Not implies. So and intelligent x. intelligent X. Okay. So there exists X, where X is boys and X is intelligent. And usually we write this statement, read this statement in this way. So there are some X where X is a boy who is intelligent. Okay, meaning like this. Or we can express like this. There exists some X and X are boys and the X are intelligent. This is called existential quantifier. So that means the implication, there is a universal quantifier. It has connected with the implication, but for existential quantifier, it has connection with and. But some properties of the quantifiers are this. That is, for universal quantifier, you can see for X and for Y, it will be similar to the Y and X. Okay, so that means the order of writing the same quantifier that is universal quantifier, but both are the same. So we can write either X before Y or Y before X. There will be no problem on it. For existential quantifier also, we can write either Y or X. But if we mix up those, then actually the order is matter. So there exists some X for all Y. This is not same as for all Y there exists some X. Okay, so that's why there is two quantifiers. When we can write, then we have to write it cautiously. Then some of the statement we can see, like we want to write in first order logic form. All birds fly. So at first we need to think about like here is which one is subject and which one is predicate. So bird is our subject and fly is our predicate. In this case, the subject and predicate, and all is our quantifier. Okay? All is our quantifier. All, yeah, that means for this is the universal quantifier. For all X, X is bird. It means that X will fly. Okay, so if X is bird, it implies X will fly. So another statement is given: every man respect his parent. So how can we represent this? So then again we have to think about that is which one is subject and which one is predicate. So here is we can say here is the man. Man is our subject, and predicate is respect his parent. So here is man. So that means it is mentioned about every. So every is all. Okay. So for all X, if X is a man, then X respects parents. X respects parents. Okay. So this is the representation. So there are some representations. So some boys play cricket. So boys here is our subject and play cricket is the predicate. So there exists some. So there exists some boys. X is boys. X play cricket. Okay. Another representation, like not all students like both mathematics and science. So student is our subject and all these are predicates. Okay. Not all. So here is all. For all X, if X is a student, not all. So if here is not all, so all X. But if we negate it, not all X. If X is a student, X like mathematics and X like science. Okay. So this kind of a statement we can represent using first order. So these are the first order logic representation. Okay.
Sir.
Yes, please.
স্যার ওখানে থার্ড ব্র্যাকেট কেন ইউজ করা হয়েছে? নট অল এর পরে। নট অল এর পরে।
হ্যাঁ, এই স্টেটমেন্টটা আলটিমেটলি এটা হচ্ছে তার কোয়ান্টিফায়ার না?
জি স্যার।
তাহলে এখানে মানে এই স্টেটমেন্টটা পুরা যদি এরকম হতো যে শুধুমাত্র এতটুকু থাকতো যে স্টুডেন্ট এন্ড এই পর্যন্ত, থার্ড ব্র্যাকেটটা না দিলে, যদি না দিই থার্ড ব্র্যাকেটটা, তাহলে কি হতো? ফর অল এক্স লাইক এক্স ম্যাথামেটিক্স এই পর্যন্ত বুঝাইতো, ঠিক না? মানে ফর অল
এন্ড
এক্স এর স্কোপটা এই পর্যন্ত বোঝাতো আর কি। কিন্তু আসলে এর এই স্কোপটা তো একেবারে শেষ পর্যন্ত না।
বুঝতে পারছি স্যার।
ওকে,
স্যার একটা কোশ্চেন ছিল স্যার।
হ্যাঁ হ্যাঁ
স্যার 3 নম্বরে তো স্যার আমরা দেখছি যে স্যার এসেনশিয়ালের ক্ষেত্রে স্যার মানে এন্ড অপারেটরটা ইউজ হচ্ছে, এখানে ইমপ্লাইজটা ইউজ হচ্ছে কেন?
হ্যাঁ, এখানে হচ্ছে আহ, আহ, যদিও হচ্ছে এন্ড স্টেটমেন্ট এর সাথে আমরা ইউজ করে থাকি আর কি, ইউজুয়ালি মেইন কানেক্টিভ, এখানে বলতেছে মেইন, ঠিক না? ইউজুয়ালি এটা হচ্ছে আমরা ম্যাক্সিমাম ক্ষেত্রে হচ্ছে ইউজ করে থাকি, কিন্তু এক্সিস্টেন্সিয়াল কোয়ান্টিফায়ারের সাথেও আমরা কখনো কখনো ইমপ্লাইজ হচ্ছে ইউজ করতে পারি আর কি। এটা মেইন কানেক্টিভস আর কি, এখানেও মেইন কানেক্টিভ। অনেক সময় আমরা হচ্ছে এই কানেক্টিভের সাথেও বা ইউনিভার্সাল কোয়ান্টিফায়ারের সাথেও দেখবা যে এটাকে ইউজ করতেছি আর কি, এন্ড কে ইউজ করতেছি, দো দিস ওয়ান ইজ মেইন কানেক্টিভস।
আচ্ছা স্যার।
Okay. So this is how we can represent also the complex sentences. Okay. Now, our last topic is about the planning. So the planning in AI, the role of planning. So planning in AI, it refers to the sequence of action. That means we can say you have to perform sequence of actions to achieve a goal. So like for the goal-based agent, we have already discussed it maybe before the midterm. So to achieve some goals, we have to perform some actions, but you have to perform those actions sequentially and intelligently. So when you make the sequence, then you have to plan. So that is the role of planning. So like if you want to design a part picking robot, so what it will do, maybe you want to design a part picking robot, and that robot will arrange some of the blocks where larger block will be on the floor, and then that is maybe the smaller blocks will be in upward directions. So there are several blocks will be there. Okay, so maybe you can say one block is this, another block is that, and another block is this one. So this is A, this is B, and this is C, and you have a robot, and then you ask that robot, okay, then arrange these blocks where the largest one will be in the floor, and the next largest will be on top of that, and the smallest one will be just maybe at the top. So what it will do, it will find out the sequence, okay, sequence of actions. Then what one it will be picked at first, and then what one will be next, and what one will be the next. Okay, so that's the planning task. For every task, specifically AI needs to make a sequence. So it needs to determine the sequence of actions. So why we need it? Because it will think ahead. So that means the planning can be maybe it kind of the thinking ahead. So it evaluates the different possible outcomes and select the best available route. Okay, best available route. Like for arranging these blocks. So it can maybe pick this one on top of B, and then these two on top of A. Or the robot can do like at first A, then the C. Okay, so that is the smallest one, and then it will see that okay, B is also larger than the C. So it should again remove the C and then pick the B and put it in top of A. And then after that, maybe on C. So that means we can see there are sequences. Okay, there are sequences, but it needs to find out the most there is the best way or best path. So if intelligent agent can planning ahead, then we can it can perform the task with optimal outcome. Then another one is adapting to change. Sometimes some of the agents may need to adapt. They need to adapt. Some of the agents it need to adapt. So if it can perform, if the agent can perform planning, then it can also adapt any kind of changes on that dynamic environment. Okay? There are several intelligent agents specifically designed for the dynamic environment. I think we already discussed about the reinforcement learning, okay, agent for the dynamic environment, and autonomous action also. So for the planning, after planning, it can perform some autonomous actions. So based on the situation, based on the current state, it will also automatically or autonomously perform the actions. Okay, so that's another benefit of the planning. There are several types of planning. Specifically, we can say 4 types: classical planning, probabilistic planning, reactive planning, and hierarchical task network planning, HTN planning. The classical planning, so already we can say that the best for prediction and well-defined for the well-defined environments. So this kind of planning, specifically the many machine learning algorithms will perform this kind of planning. Okay? So it will predict the maybe the stock price of next month, and then the AI agent will automatically invest like this way to maximize its profit. So this kind of planning is very predefined planning. Okay, the well-defined structure is there, the data set is there, and based on the data set, you will just make that kind of planning decisions. So this is the classical planning. And the probabilistic planning, sometimes we need to perform also the probabilistic planning. And for that, usually we model the problem using the MDP, that is Markov decision process. And this is best for the dynamic environments, specifically the real time. I think we have already studied the probabilistic planning using HMM, the hidden Markov model. Okay, the hidden Markov model is kind of the probabilistic planning. And we have already studied 2 of the problems. One is the weather forecasting problem, and another one is our dishonest casino model. Okay, so using some probabilistic relation, as I already discussed in this class also, the probability of initial probability, then transition probability, then emission probability. Utilizing those probability, the probabilistic planning will make the artificial intelligence agent. Then some of the planning can be the reactive planning. Specifically, the reactive planning is performed by the reinforcement learning agents. So let's say the robot wants to avoid obstacles. So one of the reactive planning can be, okay, so a robot will move and then it will stuck on the obstacle, and then it will try to avoid that. Okay, so when it will learn automatically that how can we avoid the obstacles, so that kind of planning is called the reactive planning. Okay, so it's stuck and then make the decision based upon that. So this is kind of based on reactions. Okay, So the reinforcement learning agent, it will learn from the environment automatically based on our there is reward and punishment mechanism. Okay, so when it will do the better things or good things, then we will reward that. Otherwise, we will punish it. And another one is the hierarchical task network planning. Okay, so this is kind of best for the complex task, right? If you want to design a robot for the soccer match, so multi-agent environment, it will work, and it will divide the task in different networks, and then connected those tasks, and then finally it will find out the solution. So the assembling of different parts of a machine by a robot. So those kind of tasks actually where multi-agent environment is necessary. Specifically, those kind of planning is called hierarchical task network planning. So that means already for planning, we have already studied the classical planning method in our machine learning, neural networks, and probabilistic planning we have already discussed in our HMM, and reactive planning we have discussed in our reinforcement learning. And the hierarchical task planning, this one is complex. We didn't cover in our syllabus. The last topics we want to discuss here is about okay. So we have already discussed about propositional logic. We have already discussed about our first order logic and also the planning. Now, if we utilize the first order logic and also utilize our propositional logic to prove some statements, then how an intelligent agent will form the problem, and then how it will solve that problem. There are several methods for that, and one of the popular method is called the forward chaining principle. Okay, forward chaining approach. So using the forward chaining approach, it will prove the statement. Okay, prove the statements. That is whether this one is true or not. And for that, here is given a problem. This is an example actually. So there is currently a war going on, and the United States is desperate to round up all the criminals. We want to determine whether Colonel West is a criminal. Let's start with what we know. Okay, so we want to prove that is Colonel West is a criminal. So our knowledge is this one. This is the knowledge. So we know that it is a criminal, it is a crime for an American to sell weapons to hostile nations. The country, no, just say the name of the country. Country is no, okay, is an enemy of America. Furthermore, we know that Nono has some missiles, all of which were sold to it by Colonel West. So Colonel West sold those weapons to Nono, who is an American. That means Colonel West is an American. Then represent your knowledge base using the first order logic. Okay, first order logic, and then you can use the following function predicates like American X, criminal X, hostile X, missile X, weapon X, X enemy of Y, X owns Y, X sells Y to G. So these are the given things. Okay? And then how can we represent this one? Specifically, we want to prove this. We have this knowledge. So at first, what we have to do, we have to represent this knowledge using some knowledge representation form. And this is the first order logic knowledge representation. Okay. So here is, we can see there is the clues are given. Okay. American X. So we know that it is a crime for an America to sell weapons to a hostile nation. So if we can say American X is American, and Y is the weapon, and X, that means the American sells Y's weapon to G. G is maybe some nation, okay? And if G is hostile, because it's a crime to sell weapons to hostile nation, so G is hostile. If those are the conditions, so then we can determine that, okay, X is criminal. Okay, so the country Nono is an enemy of America. So we can represent that statement here. Okay, the enemy Nono is an enemy of America. Then the Colonel West, who is an American. So here is the representation for that. The West is an American. And we can see Nono has some missiles. So owns, we can see Nono owns M. And M is missile. Okay, all of which are sold it by Colonel West. So that means Nono owns X, and X is a missile, and West sells X to Nono. Okay, and okay. So here, based on this, that is missile X are the weapon X. Okay, missile X actually the weapon X. Then based on this representation, we want to prove that that is the Colonel West is criminal. Can we prove it? Using the forward chaining, we can prove it. So here the missile, that means at first we need to write the atomic statements. Okay, so atomic, here we can see American West is American, Nono enemy of America, and missile is M. So here this is missile M. Nono owns missiles, and Nono is enemy of America. And then we can see that is for this statement, the missile M and owns Nono M. So missile M and owns Nono M. So two things. So if we can add these two things, missile M and Nono M, so this is missile M, this one missile M, and Nono owns this X. X is a missile. Okay, so if we can combine these two in AND notation, it means West sells X to Nono. So here is this. That is West sells M to Nono. Okay, now weapon M, there is missile M. Missile M is weapon M. So here is you can see missile X is weapon X. So here is the missile M is weapon M. And another enemy of Nono, Nono is an enemy of America. So what it implies? Nono is an enemy of America. So X enemy of America is hostile X. Okay, so here's this. That is X, here is Nono. Nono enemy of America. It means hostile Nono. Okay, now if we combine all this, that is the utilizing this one, American X, weapon Y, sells X, Y to G and hostile X, then we will see this is American. So that means here is the West is American and M is weapon and West sells M to Nono and hostile Nono. If we combine these two in AND notation, it implies that the West is criminal. So this is called the forward chaining approach for finding out the inference, okay, finding out the inference from a statement. So at first, from that statement, we have to represent this one using the first order logic. And then first, from the first order logic, we can apply the forward chain or maybe the backward chain also to find out the inference, okay, the inference. So here inference is proof that West is a criminal, utilizing all those first order logical statements or first order logical knowledge. So I think that's all in our today's lecture. So do you have any question or queries?
আচ্ছা স্যার, এই টপিকটা থেকে কি যে লাস্ট যে এক্সাম্পলটা দেখালো এরকম সিনারিও বেসড কোয়েশ্চেন থাকতে পারে, রাইট?
হ্যাঁ, সিনারিও বেসড কোশ্চেন থাকতে পারে, তবে কমপ্লেক্স হয়তো দিব না, ঠিক না? কারণ আমি এটা লাস্ট লেকচারে দেখাচ্ছি, ডেফিনেটলি হচ্ছে তোমাদের হাতে সময় কম স্টাডি করার, এটা আমি বুঝি। হ্যাঁ,
ওকে স্যার, থ্যাংক ইউ।
স্যার আমাদের কি কিছু স্যাম্পল কোশ্চেন দেওয়া যায়, দিলে ভালো হতো আর কি স্যার।
স্যাম্পল কোশ্চেন আসলে এআই কোর্সটা এমন কোর্স যেটাতে স্যাম্পল কোশ্চেনের অভাব নাই। আমরা ফলো করতেছি সেটা হচ্ছে রাসেলের বুক, স্টুয়ার্ট রাসেল। হ্যাঁ, প্রত্যেকটা চ্যাপ্টারে একাধিক এক্সারসাইজ আছে, কি বুঝতে পারছো?
জি স্যার, বুঝতে পারছি স্যার।
হ্যাঁ, জাস্ট এক্সারসাইজ গুলো দেখো, প্রচুর কোশ্চেন।
তো স্যার, রিইনফোর্সড লার্নিং এ যে আমাদের রিওয়ার্ড যে ম্যাট্রিক্সটা ক্যালকুলেট করা লাগে, আমাদের কিউ অ্যারেটা কি ফুল ক্যালকুলেট করে দেখাতে হবে?
না, ওখানে যদি পরীক্ষায় ফুল ক্যালকুলেশন তো আসলে অনেক সময়ের ব্যাপার, ঠিক না?
জি স্যার,
সেজন্য
হ্যাঁ,
পরীক্ষায় সাধারণত দেখা যায় যে বলে যে ঠিক আছে তুমি কিউ এর দুটা স্টেপ হচ্ছে করে দেখা, জাস্ট দুটো আপডেট তুমি করে দেখাবে। সেটা র্যান্ডমলি হতে পারে, সিকোয়েন্সিয়াল হতে পারে, বলতে পারে যে সিকোয়েন্সিয়াল দুটা স্টেটমেন্ট অথবা র্যান্ডমলি দুটা হচ্ছে স্টেটমেন্ট আপডেট করে দেখাও।
ওকে স্যার।
আর কোনো কোশ্চেন বা কোয়েরি তোমাদের?
স্যার আমাদের দুই একটা টপিক কি কমানো যায় স্যার? ওই দিন দুইটা এক্সাম আছে স্যার, ব্যাক টু ব্যাক, মানে আজকে যেগুলো পড়াছেন স্যার ওগুলো পড়া অনেক টাফ হয়ে যাবে।
হ্যাঁ, সেজন্য এখান থেকে কোশ্চেন খুব সহজ করার ট্রাই করব আমি। কিন্তু তোমাদের যদি কমানো যেতই, আমি আসলে আজকে লেকচারটা নিতেই চাচ্ছিলাম না তোমাদের। আমিও বুঝি যেটা লাস্ট ডেতে পড়ানো এটা ভালো না, ঠিক না, কিন্তু তারপরে যেহেতু সিলেবাস আছে এবং সিলেবাস তুমি তো জানো যে ওবির সিলেবাস যেটা সেটা কভার করতেই হয়, ঠিক না? আমরা কোনোটা স্কিপ করতে পারি না। তো সেজন্যই আলটিমেটলি মানে বাদ দেওয়া যাচ্ছে না, আমি চাইলেও যাচ্ছে না সেটা।
স্যার তাহলে কোনোভাবে কি এক্সামটা পিছানো যায় স্যার? মানে পড়া একটু
পিছাবো
বেশি।
কেন? না, পিছানোর তো কোনো দরকার নেই মনে হয়।
স্যার পিছাইলে আমাদের জন্য একটু সুবিধা হইতো, আমরা টপিকগুলো ভালোভাবে কভার করতে পারতাম।
আমার মনে হয় না যে পেছনে কোনো অপশন আছে
স্যার
আমাদের।
থাকুক স্যার, কারণ স্যার আমাদের স্যার এক্সাম ছেড়ে স্যার আবার স্যার মঙ্গলবার স্যার আমাদের অন্য এক্সাম আছে স্যার, সো ওইটা ঝামেলা হয়ে যাবে।
স্যার তাহলে
স্যার আপনি
মানে আজকে
একটু
টপিকগুলো
ইজি
যেহেতু পড়া হচ্ছে আমাদের কি পরীক্ষায় এই টপিকগুলোকে স্কিপ করা যাবে না, আমরা পড়ে রাখলাম, কিন্তু অনেকেরই রবিবারে 2টা এক্সাম, তো কালকে একদিনে আমাদের জন্য পুরাটা ইয়া করা কঠিন, আবার মিডের মার্কিংও আমাদের দেখা গেছে খুব অ্যাভারেজ আর কি। তো আজকে টপিকগুলি যেহেতু আমরা মোটামুটি ক্লাস করেছি বুঝি, কিন্তু ফাইনালি যদি স্যার এই টপিকগুলি অফ রাখতেন তাহলে আমাদের একটু সুবিধা হতো।
না, আমি তো বললাম তোমাদের, আমি পার্সোনালি অফ রাখলে সমস্যা নেই, কিন্তু কথা হচ্ছে ওবি এর কারণে সেটা অফ রাখতে পারতেছি না আমরা। কোনো টপিক যেটা সেটা স্কিপ করা যাবে না, সেখান থেকে হয়তোবা আমি ওকে কোশ্চেন ইজি করতে পারি, দ্যাটস ওকে, কিন্তু স্কিপ
স্যার
করা যাবে না।
ডিফিকাল্টি লেভেল ইজি করলেই হবে কি এটাই?
হ্যাঁ, আমার মনে হয় যে লেকচার যেটা আছে, যদি অন্য কিছু নাও দেখো, শুধু লেকচারটাই দেখো। ঠিক আছে?
স্যার
আগেন
আমাদের
আমার সম্ভব হলে আমি কমাইতাম, হ্যাঁ আমি পারতেছি না বলে, বুঝছো না, কারণ এখানে হচ্ছে তোমার ওবিএস সিলেবাস যেটা, সেটাতে সবাইকে একই সিনক্রোনাইজেশনে থাকতে হয়, সেক্ষেত্রে আলাদা করে সম্ভব হয় না আর কি, বুঝছো না, কোনোটা স্কিপ করার।
স্যার আমাদের কি থিওরি টাইপ কোশ্চেন থাকবে?
থিওরি থাকতে পারে, আবার ইয়াও থাকতে পারে।
স্যার আমাদের স্যার ডিরাইভেশন থাকবে না স্যার, লাইক আপনি আমাদের বিটার বাই অ্যালগরিদম ডিরাইভেশন দেখিয়েছিলেন, ওগুলো তো থাকবে।
ফুল ডেরিভেশন হয়তো থাকবে না, ডেরিভেশনের ভিতর থেকে 1-2 মার্কসের ছোট কোশ্চেন থাকতে পারে, আর প্রবলেম হয়তো বাকিটা।
স্যার 1-2 মার্কসের ছোট কোশ্চেন কি স্যার থিওরি বেস হবে?
হ্যাঁ, ইউজুয়ালি তো তাই হয় না।
স্যার তাহলে তো স্যার আমাদের সানডেতেই ফাইনাল হচ্ছে তাহলে।
হ্যাঁ, সানডে ফাইনাল, যেটা তোমাদের ডিপার্টমেন্টের রুটিন যেভাবে আছে ওভাবেই।
জি স্যার, থ্যাংক ইউ স্যার।
ওকে, ভালো থাকো তাহলে সবাই, আল্লাহ হাফিজ।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম
আসসালামু
আসসালাম।
আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।